I didn't do the recursive coding ahead of time, so you will have a chance to go over it. Yesterday, on Tuesday, Thursday section, we had an internet failure. I did. So I had to end the meeting, start all over again. My students were having so much fun signing in and out. They were super cool about it. And Olivia is one of our TAs. She was explaining, hey, Anse is going through internet troubles. Just hang in. And they did. They were hanging in and out. So, you know, you never know what's going to happen. It's all depending on the internet. And I do pay for a fast speed internet. Trust me on this. I didn't want to take any chances, but I can't control everything, you guys. All right, so I'm gonna start sharing my screen. I'm hoping everybody is doing a great job with the time management. Time management is everything in this class, everyone. Like I repeated several times, create a routine, stick with that routine. I say the same thing to my kids who are around your age. They are still students. And I tell them to stick with a routine. However nerdy it may look to you or to a person outside, you don't care. Sticking with a routine will give you the sense of normalcy, especially during these tough times. You need that sense of normalcy. So stick with your routine, start early. I know that our help hours are getting busier and busier. So let's get started on sharing screen. We have quite a bit of material to go over. Recursion, your favorite, my favorite. Writing recursive codes are not difficult. You will find it in our second project that we are going to post this Friday. You're going to find it to be fun because we're going to give you a singly linked list this time. And we're going to ask you to be able to add to this data structure, but write your algorithm recursively, remove from this data structure, but write your algorithm to be able to remove a node recursively, search recursively. Everything you're going to do in this project is recursive. If you're giving me a non-recursive method, you get 0 out of that method, including its test cases. So, you know, you're going to deliver everything recursively when we release project number 2. So don't confuse it with project number 1 or any other things, okay? So writing recursive methods are easy, relatively easy, because if you're going to have difficulty, I don't want to undermine that. Analyzing it becomes a little bit of tricky. So let's talk about recurrences. Before I get into recurrences, I'm going to post this on item pool. I didn't get a chance to, I prepared a question, didn't get a chance to post it for recursion. I have a question for you to review what we have covered. What do you think about my statements here? And then you're going to tell me true or false. Right now, I want you to just turn your microphone on. Oh, a big theta bound will exist for every function. Do we get big theta for every function? True or false?
False.
False.
False. Thank you. Awesome. We don't get big theta for every function. Take a look at our is prime. If you notice that at most it was linear, at least it was constant. So since the big O and the big omega did not agree, they must agree in terms of the runtime function. We could not assign a theta statement for that. One possible best case for adding an element to an empty list is when it is empty. True or false?
False.
False.
False. We are looking for at least one data input size to be able to analyze a best case, worst case, so on and so forth. We only use big omega for worst case analysis. True or false?
False.
False. Thank you.
False.
Oh, look at how awake you are. Wonderful. Yes, big omega cannot be used for worst case analysis. When we are doing best case, worst cases, that is the third dimension. They have their own runtime function analysis. They will have the big O, big omega, and the big theta. If a function is big O of n squared, it cannot be also big omega of n squared. True or false?
False.
False. Yes, you're recalling the definition. Take a look at our inequality. There was that equality there in our definition. So go visit your formal definitions for big O, big omega, for my students who are still questioning. I am planning on hosting a study session, most likely on Sunday. You will hear that from me. Absolutely voluntary for you to come. I will record it. Even if you don't come, I'll just teach it to myself and then record it and put it on Piazza. I think it will be good for you to go over a few examples. Absolutely voluntary, not mandatory, because I know it's Sunday. And Sunday is fun day, and I don't know how busy you are. Okay, so that's something that I wanted to go over with you. With that, let's start analyzing recursion. Okay, big picture. When and if we write a recursive code, one of the categories that it will fall into, one of the most common category as a software engineer, as a programmer, we target is to be able to write a recursive code that halves the input size every time it iterates. Halving the input size, or third of the input, or fourth of the input that you're processing, whatever. But our goal is to be able to cut the input size every time we make a recursive call. The most common algorithm that I can teach you, something you may have learned and implemented in your early programming classes, is binary search. So that's an excellent example for me to show you how a recursive algorithm is written, and it cuts the input size every time I make a recursive call with my new container, only the half of the size to be searched for or processed for. So halving the input is one way of writing a recursive code. And that's usually our goal. We would like to do that. That really helps us with our runtime. Number two is the most common, is the constant size input, which is what you're gonna do for your project. When we give you project number two, I'm referring to project number two, don't confuse it with project number one. That has nothing to do with recursion. So don't you be worrying on going on Piazza, oh my God, she asked me to do things recursion. No, that project number two, you're gonna work with constant size input, giving you the singly linked list we ask you to process. You are going to iterate through, adding an element or removing an element, searching an element. You're going to do that recursively. So every time the size of your linked list is going to shrink by one. You start out with the constant size, and then it just shrinks by one. And then we'll talk about that, what type of algorithms actually fits into these when and if we write a recursive call. Another one, which I hope that we stay away from, is writing a recursive code that's doubling the input, like the Fibonacci, the famous Fibonacci recursive function. That's something I will cover the last. So let's go over these concepts, and let's talk about binary search. So here is my binary search algorithm. This algorithm has already given to you under week 2. So if you go to D12 week 2 source code, there is binary search there. If not, send me a notification on Piazza. Hey, Anse, you forgot to put binary search. I'll put it there because it's in my slides and I want you to have it as a Python file. In fact, I'm going to show it to you right now as we debug through it. Okay, so the binary search, look at my parameters. Now, this is quite a busy function. It has 1, 2, 3, 4 parameters, okay? And I'm passing the container. That's my data, that's my Python's list, along with the target value that I'm searching for. And I have 2 additional parameters that I'm keeping an eye on for the, as I partition my given container into halves, I'm keeping an eye on the indexes from the beginning and then the end of that container. So that's what the low and the high is for. So if the index of low surpasses high, we are done. We are going to return false. We didn't find what we are looking for. We went through the whole list. We didn't find what we are looking for. Otherwise, what we are doing is cutting the array by half, okay? Cut the array size by half, and then check out if we are actually targeting, if the mid element happens to be the target value or not. If that is the case, then we will say, yeah, we found what we're looking for. If it's not the case, binary search only works accurately if your container is already sorted. My container is my Python's data, Python's list. That's a Python's list, and the container is already sorted. You only work with binary search if you're receiving a sorted data. That's how you get a correct output, okay? So it would be a good thing for you to check in your code before you call your binary search, is the data sorted or not? Check that before you call your binary search. Otherwise, it's going to report wrong results. Okay. So based on this being searched, we checked against the middle value. Is the target value less than the middle value? Then search to beginning of your array up to that midpoint recursively. Cut it again in mid and check it against mid. Is this less than? Cut it again. Check it again with the mid element. Cut it again. You're going to be cutting it every time to find out if that is actually the case, until you can cut no longer, and then you will report it that you either found it or not. If the value is greater than, you're going to work on the other half of the array from midpoint to the end of your array, or Python's list. I use those terms interchangeably. So, Python's list array, you get the idea that I'm working on a sorted container. So keep cutting it in half. Check it with the midden element. Is that the target value? No. Cut it again. Is this greater than, less than? If you didn't find what you're looking for, cut until you can cut no longer. So that is my algorithm. Let me quickly show you if I can pull my PyCharm up here. I should have my binary search somewhere here. Yes, so this is my recursive binary search. Like I said, it should work on a sorted list. So make sure that your algorithm is sorted. What I'm doing is just simply invoking the recursive algorithm. Let me run it real quick to make sure I'm playing with the correct one here. You can see my PyCharm, correct? It shows me that I'm sharing the screen. Am I correct?
Yeah.
Yes.
I'm seeing
Yeah,
picture.
thank you.
Yeah.
Thanks for the feedback, everybody. So I'm going to put a breakpoint. I did a example of how to put a breakpoint if we have given you a coding challenge, how to download, open it up on CC1 and put a breakpoint to test your unit tests. That's under week 2. For those of you who are struggling on what to do with when we give you project coding challenges, how do you test it locally? So check it out. It's a very short video, you guys. It's under week 2. Take a look at it. I also put it under course tools too. So there are a lot of tutorials for you to learn how to debug. I'm going to put a breakpoint where I'm calling the function. So in CC, in coding challenges and projects, when you're going unit test by unit test, pick a unit test, put a breakpoint where you're calling a particular function that you test for. And you will see that in that video. It will take you to your code and show you where it breaks. So I put a breakpoint where I call it, I right mouse click, and I say debug. So it will get me into that debug mode. The debug window activates. It highlights the code. It waits for me to either step into. You can use your keyboard. I'm a Mac user. Function F7 is step into, or you can use your blue arrow on the debug window to go step into, or you can do step over. It's up to you. There are different opportunities for you to run to the cursor, play with it. Go ahead and play with these. I will do a step into, so function F7 takes me to my recursive code. It says, okay, the target you're searching for is 78. And then it says, okay, is the low index is the beginning of our array is 0. The high index is the 15th. Is that one greater than the high? In other words, did they crisscross? No, they didn't. So find the midpoint. We will find the mid index. Mid index is 7th. Check it against the middle of your value. Is the 7th index what you have in your container happens to be the target value? If it is the case, you're done. Return true. It wasn't the case. It was not 78 at the 7th index. We looked at it. You can always do this, add watch, like highlight what you want to watch. Highlight what you want to watch, and you can only do this during debug mode. Right mouse click, say add to watches. And that way you can actually see what was in the midpoint that you were comparing against. And it turned to be false. Obviously, it was 14, and that is not 78. So therefore, 78 is greater than 14. You're going to work on the lower side of your array, your Python's list. So that's why it falls into the else, because it's going to look for the lower end. Add 1 to the midpoint, mid plus 1 through the end of your array, search for it. Did the low index surpass the high index? No. Low is 8, high is 15. That's false. Find the new midpoint. Note that when we start looking 0 through 7, 0 through 7 has been already disqualified. I am never going to go through that part of my array ever again. I already cut the input by half by simply doing that mid operation. I already disqualified 0 through 7th index of my array or of my Python's list. So therefore, I'm only working with this half. In this half, I'm looking at the mid element in this part of this array. And I find out, is this in fact 78? No, it turns out it is 25. Look at my debugger. It shows me that it is 25. So therefore, is 78 greater than 25? Yes, it is. Cut it again. Cut it again. This time, you're going to be working from a different point. Midpoint was 11. So you're going to start from 12 through to 18, right? And so now you cut it again, that portion of your array is gone. So you're now only working from the index 12th. You can see that low index through the 15th, and then cut it again. And eventually, obviously, you will see that it's not there. It's going to report false. Come back here and say, I didn't find what I'm looking for. That's pretty much, you can write it here and there slightly differently. That's how general behavior of a binary search is. You're always looking for that midpoint, checking against the target value. Did I find what I'm looking for? No. Is the target greater than what I'm comparing to? Yes. Then search the lower half of the array. Cut it again, find it in the middle, check it against the target value. Is this greater than or less than? If I didn't find it already. No, I didn't find it and it's less than. Then work only on the top portion of that half array that you already cut it from the previous call. That's what's going on. So how do you analyze something like that? Let me go back to our presentation. So this was our binary search. I'm guessing everybody is able to see my slides, so I'm moving on here. So how do I analyze it? When we give you a recursive algorithm, you have to have a algorithm you decided to write recursively. A part of your algorithm will cause your algorithm to stop calling itself, because recursive functions mean that it is a function you're trying to write that keeps calling itself. That's what recursive function is. So I'm hoping you were exposed to some sort of recursive function on your earlier programming classes. If not, you kind of need to do a little bit of a introduction to yourselves before you start looking into binary search or any other recursive function that I'm going to teach you here. But if you write a function that keeps calling itself, that's a recursive function. You cannot keep calling the function forever. You have to find a condition for it to stop. As the input size shrinks, you have to find a way to stop this function calling itself. For me, for binary search, I need to cut it in half, check it against the mid element. If I didn't find what I'm looking for, I'm either working on the upper half or the lower half. Then I take whichever half I can work with. I take that and cut that in half. I take that and cut that in half. Every time when I cut it in half, I'm checking, did I find what I'm looking for? That's my base case, because if I find what I'm looking for, I'm going to stop calling it recursively. If I keep searching and I don't like what I'm looking for, the indexes will crisscross. Low will exceed high, therefore I will stop. So those, that parentheses I put around that section is what is going to cause my algorithm to stop. So therefore that is considered to be my base case, where the algorithm stops calling itself. My recursive case is where I'm making the recursive call. it's either one of them. I'm either calling it else if the target is less than, call the upper side of my array, or target is greater than, call the lower side of my array. So either one of them gets to be invoked at one time. So it's not two recursive calls that you're making back to back. It's one of them, because it's going to be true for one of them. Either the target is less than, target is greater than. Okay. So one thing that I want you to pay attention to when you are writing, if you decide to write a recursive algorithm, the input size must shrink. If you are not shrinking the input size, don't write it recursively, because you're not going to be able to stop. You have to find a way to stop your recursion when the input size becomes 1 or 2. You're going to see that in our merge sort. So you have to find a way to function to stop calling itself. So in visualization, what I just showed you on the debug window is what I'm showing you on the slide here. Imagine that I have this list. It's already sorted. Binary search will work accurately only and only if the list is sorted. So I check and trying to find for value 42, I guess. So that's what we are looking for. Target value is 42. So we will cut the array by half and then check with the middle element. 42 is greater than 30. So that portion of the array 0 through 8, the index 0 through 8 is gone. I'm never going to get back there. Why? 42 is greater than 30. I'm only going to work through 9 through 16 and then find that mid element again. Okay, 56. Well, is that 42? No, it's not. So lower side of that array is gone. I'm never going to see that again. I'm never going to work through the indexes 13 through 16, but I am going to work through 9 through 11 and eventually find out that I have actually found, and I will return, yes, we found it. Binary search, you can return the index, you can return true, false, depending on how you're writing this. And eventually our code will report it back and say, yeah, we found what we're looking for and it was here. Okay, so that's how the binary search is working. Do you see how I highlighted the portion that I'm never going to deal with? I should also highlight the portion that I am never going to deal with through indexes through 13 through 16. And there you go. So now the question is, okay, what kind of algorithm did I write? So how is this really growing? Is this a linear function that I have written? I got it, that I have written it recursively. But how am I going to consider its runtime, right? And in your opinion, this is a search function. What is the best thing that can ever happen to you? This is a question for you, everyone.
Wouldn't it be that you like
The first one is the
Yes.
The target value is the mid.
Yeah. So the target value that you the first time you run, the target value that you find is in the middle. Done. Right? That's the best case that can happen to you. All of you who are contributing, I thank you. What is the worst thing that can happen to me?
It's not in the list.
Not in the list. Any other worst case that you can think of?
It's the last element in the list.
Yeah, the last element in the list. But it is the worst case is that I just keep cutting and cutting that and I didn't find what I'm looking for. That's the legitimate, the worst case that we have to think of. And having the input, I don't know. What should I call and how should I represent my worst case with a runtime function? I got the best case, big omega, big O, and will agree that they are both constant. So I will have a big theta for it. For the worst case, I have no idea. So I start thinking. I start thinking mathematically. I am given an array size, a Python's list. Like I said, I use those terms interchangeably. I am given an array size of n. I'm eliminating the half. I'm going to keep doing that until I have only one element remains. So the behavior my algorithm shows start with n over 2, n over 4, n over 8. You know, keep dividing, dividing. And then I have 4, 2, and then finally 1. Then I ask myself, right? because I don't want to go too deep. I said, well, how many divisions does that take? You know where we are going. I know students who are coming from the math background, they say, oh, I know where she's going with this. Yes. Okay, how many divisions does it usually take? How do I represent it? How many divisions does it take for me to report it that I found it or I didn't find it? Okay. All right, let's reverse it. Look at it from the other direction. How many times do I have to multiply by 2 to reach n? Let me write it in different ways. 1 times, 2 times, 4 times, 8 times, n over 4, n over 2, n. Okay? So if I assign the number of multiplications to be x, then I can represent 2 to the x will actually get me the input size that it's given to me. Then from mathematics, you guys know where we are going. We can answer the top question. How many divisions does it take? If 2 to the x is going to get me the input size, then x is going to represent the number of divisions. So how do I isolate x? I take the log of both sides, right? And it becomes log base 2 of n. So that will report you how many divisions it will take. So therefore, because we are cutting the data by half, pay attention that half is why we are in log base 2 of n. Okay, if I cut the data by third, then it would be log base of 3. All right, so don't take it granted. Because we are cutting it by half, it gives me the representation for binary search to be logarithmic complexity class. So what we do is when we try to graph things, those of you who have done a lot of graphing on your earlier classes, such as physics, right? And my computer engineering students will agree that it is the inverse of exponentials, right? When you're trying to graph it. So usually y equals to log b of x, with the same thing as saying b to the y is actually x. So 2 to the 2 is 4. 2 is equal to log base 2 of 4. So you guys know how to do these. I hope that it is slowly coming back to you because we use quite a bit of simple definitions of math in order to analyze it. So we have concluded that our code actually, in fact, grows logarithmically because I'm cutting it by half each time. And how many divisions do I have to make? It turns out that I can determine that by log base 2 of n. So what I say is, for the best case, like you guys agreed with me, first element matches. Now this is true for any input size. So it's not fluctuating like the is prime, okay? It is always true that I'm gonna find it as the first element when n equals to 1, n equals to 2, n equals to 3, n equals to 1 million. It's always finding it the first time it cuts it, the target element is there. So therefore, I write my runtime complexity to define the best case with the class of constant theta of 1 to represent the best case, okay? Because the big O and big omega agrees. For the reverse case, we did not find what we are looking for. So therefore, we keep dividing. I keep dividing, I keep dividing, I keep dividing. And then I find out that I can show the number of divisions, the representation of the number of divisions is shown as log base 2 of n. And that is agreed as a big theta of log n. So my binary search, for the worst case, it is theta of log n. For the best case, it is theta of 1. That's great. But you know, where is your polynomial? You're probably asking, Professor, I say, this is great, this is super easy, but I feel like you jumped from the code, you just took the code, and now you told me that you're cutting it by halves, ask me the best case, ask me the worst case, ask me to represent it. What happened to your case analysis? You're right. How do I represent this code? You told me that I am supposed to give you a polynomial. Where is your polynomial? You're probably wondering, you skipped a step, and you are absolutely right. We just jumped from binary search, our code, to asymptotic analysis, spoiled the ending, but we never represented our algorithm with some sort of a formula, like you and I refer it as a polynomial. So let's work on that. How do I do that? Where is my function? What would it look like? Now we kind of got the idea on looking at a loop. You have seen me showing you a couple of examples such as is prime or printing a value, looking for a maximum. I kind of know what I'm doing to generate f of n. Since we are in the recursive domain, you're going to see me using t of n instead of using f of n. It's the same thing. It's the function that represents my algorithm. Okay, so stay tight. So here is my algorithm. Now I say, okay, let me try to analyze this like I did in my earlier lectures. Now I want you to slowly phase out, everybody. Phase out from the +2s and 5s and 7s and 8s. Don't get bogged down with those because I really don't care. Okay, if you're off by +1, +2, it's not going to affect, as long as it doesn't affect the degree of your polynomial. So I'm going to slowly introduce you to phase out of that +2 and then represent it as a constant operation, such as theta of 1. So here I'm checking if low is greater than high, return false. So there are a total of 2 operations, comparison plus the return. 2 operations, like I said, but I'm not too worried. If you even wrote +1, I will take that. That's correct. What you're saying is to me, that's a constant operation. So the constant operations are represented as in our in coding, in code analysis between your peers. Either we use C for any constant, or C sub 1, C sub 2 if you're assigning it to a line number, or to be more general, we say that's theta of 1. You're going to hear your colleagues saying that. Then the question is, so are you telling me in a piece of code you have segments, you call their complexity class? Yes, that's what I'm telling you. That first 2 line is considered to be constant. How do I represent? What kind of complexity do I use to represent constant? Theta of 1. I use that symbol. Okay, it's a class of theta of 1. That's what you say. So that's that. And then I have if I find the target matches the mid element to be returned true, that's +2, but I'm going to phase out and say that's theta of 1. And then I have my recursive case. And then I have a non-recursive work there where it says, the computation of math, middle element, but since it's within the else block, I will still consider it part of being the base case, okay? But usually we will refer that as the non-recursive work. So if I have like assignment, plus, and the division, there are 3 operations, and that's non-recursive work, and that's also constant, okay? So how am I going to represent this in a polynomial? Do I have any kind of representation? Yes. Here is what we do. This is an example, not matching the binary search, a generic example of a recursive algorithm. You have to write a recurrence relation. Recurrence relation is represented as an equation. Simply gives you an understanding on what's going on in your recursion. If and when I write a recursive code, I have to be able to communicate with my peers. This is what's happening. I have to have at least 1 base case. It's possible that for you to have more than 1 base case, not a problem. You will include that in your recurrence too. But at least 1 base case. And when does that become true? Does it become true when the input size becomes less than 3, less than 2, or when the input size becomes 0? How do you represent that base case? So you're going to look at your base case, and you're going to look at what's happening with your input size. When does it hit the base case? And you say, I will hit the base case when n stands for the input size. Say, for example, this is a general recurrence. This is not representing binary search, to be clear. I will hit the base case when my input size becomes less than 3. I have 5 operations to do, or drop the 5 and say I have constant operation to do there, theta of 1. Okay, So you can either put the actual number of operations, which I don't care for, and the MIT doesn't care for, put the complexity class and say when my input size is less than, say, 3, I have constant operation to do, theta of 1. And what about your recursion? Okay, so here's what you're going to say. Well, the function calls itself, right? And we're going to go through binary search in a second. Function calls itself. How is it calling itself? For my binary search, it was cutting it by half. For this example, it's also cutting it by half. Cutting what by half? Input size. Input size is being cut by half, then it calls itself. So when it calls itself, we say T of n over 2, T of n minus 1. That's how we represent recursion. How many times does it call itself? Well, in this algorithm, apparently I have 2 consecutive calls. So there are 2 calls here. 2 recursive calls that cuts the data size by half, plus some non-recursive work. Non-recursive work is 10 operations, but I really don't care for that either. You can put theta of 1 there, okay? So now, that is my recurrence. It is an equation that represents my recursion. Because you go on Piazza, you use these terms wrongly. When I write a recursive algorithm, I must generate a recurrence. Recurrence is an equation that represents my recursion. So don't confuse recursion with recurrence. Recurrence is an equation. Recursion is a function you have written that runs recursively. Okay, so now let's take a look at what we are trying to do here. We will say, okay, here's my binary search one more time. Sticking with the number of operations that we have talked about. Okay, let this low greater than high plus return false happens to be +2 operation, and checking if it is actually the target, that's +2. 2 plus 2 is 4. If the input size is less than 2, I have total of 4 operations. It's going to be either that or that, so you have to add all those operations, so it's 4. But like I said, I don't care for 4, 5. You could have put 6 there. I don't care. You're going to put theta of 1 eventually. And then check this out. I have recursive case, and I have that non-recursive case where I'm doing the algebraic operation. My recursive case is not 2 consecutive calls, you guys. I will ask this in an exam. You guys always put 2 in front of it. It's not 2. It's going to be either one of them, because it is an else if recursive call, else recursive call. One of them must be true. So I cannot put 2 in front of T here. Don't make me trick you. I will trick you. I'm glad you came to the class because I'm telling you what's going to be on the exam. For those of you who attend class, you always do real well because I'll tell you what I ask you in the exam. Okay, so 2T over 2 is wrong for binary search because it's going to be one of them. One of them is going to be true. And how am I calling this again? I am calling this every time I call, I cut the data size by half, n over 2. All right. And do I have non-recursive work? Yes, I do. And what is it? It's 3 operations. But like I said, you can put theta of 1 there, and that is perfectly fine. Okay. Oh, my internet connection says that it's unstable. So if I lose you, don't get lost. I'll log back in. Okay. So, so we look at it. We look at it again. I say, let that base case, there are 2 base cases. Let that base case to be theta of 1, where I'm making a comparison. Let the second part of the second base case to be theta of 1. My non-recursive work algebra, that's constant work. Let that be theta of 1. Then this is what your colleagues will do. This is how you, with your peers, are going to communicate. This is what we care for. We say, oh, so I have written binary search. Here is my code analysis. Here is my recurrence. N is less than 2, constant operation, theta of 1. Do you see how simple that is? And recursive case, make a call to yourself with n over 2, 1 recursive call, because it's one of them is going to be called at one time, not 2 consecutively. The reason I'm saying that, I'm preparing you for merge sort. In merge sort, it's 2 consecutive calls. So the recurrence is going to have 2 in front of it. Here, it's not consecutive. It's one of them true. T n over 2 plus some non-recursive work, constant. That non-recursive work you're going to see in merge sort doesn't always have to be constant. Sometimes we have loops. Yep, we have loops, and that will change. That will change your complexity as well. So this now becomes my representation for my algorithm. Now, I told you there's a reason why you're taking this class. Your job in 331 until the end of April, I think that's how we're going to go this semester, right? That looking at an algorithm, figuring it out, its analysis, code analysis, line by line, figuring out which class it belongs to, asymptotic analysis. We're going to do this again and again and again. Every data structure I teach you, you're going to take it, analyze it, find its complexity class. That's why it's the whole semester. It's never going to get away from you. So why is it important? Why am I teaching you recursive analysis right now? Because I'm going to teach you trees in 2 weeks. We're going to talk about binary search trees. I'm going to give you a project on AVL trees. And they are all recursive, you guys. All of them, the functions that you're going to write, majority of them are going to be recursive. So therefore, you need to be able to model your algorithm to analyze what's the complexity. Where does it fit into? So now I have my equation. We kind of spoiled the ending. We used math as our friend, and we said, okay, this is logarithmic. But usually you will end up with a recurrence, and it's not going to be that easy to solve. So we need a way to solve this. And the way to solve it for certain recursions, it's called the master theorem, which I'm going to teach you today. And you can solve this on the fly. And a lot of our recursive algorithms will fall into this category, lucky for you. So you can use the master theorem on the fly to determine the complexity of your runtime complexity of your algorithm. And that will come in really handy for you in your future program writing and your interviews too. So I cannot wait to teach you that. All right. Let's take a look at an example. Let's get you a little bit into thinking. Here's an example, very dingy recursive function, recurse, n is being passed. If n is less than 3 for some odd reason, we are returning 80. Who cares? That's a recursive algorithm. Let's not judge what it's written for. And then I have this variable called a. I'm multiplying n by 2. And then, it's there for a reason. Who knows why? Doesn't matter. Then we have value 1, recurse n divided by 3. Value 2, recurse n divided by 3. Return the value by adding val 1 to val 2. Okay. How do we analyze? How do we come up with its function, recurrence, that represents this algorithm? The name of the algorithm is recurse. Recurse calls itself when it's being assigned to val 1 and val 2. So there are 2 consecutive recursive calls that I'm making, one after another. It's not in a condition block. So I start looking at my code line by line. I'm looking at, so that's where I'm going to stop. When n equals to 3, I'm supposed to terminate my recursion. That is my base case. And then I look at my arithmetic operation where I'm multiplying something with 2 with the assignment. That's plus 2, but I don't really care. Let's represent that as theta of 1. My base case contains 2 operations, but let's just represent that as theta of 1. I have recursive case, and then I have non-recursive work right there at the bottom. So adding 2 values and returning 2 operations, that is theta of 1. So basically, what we have is to represent our recursive call. Our recursive call is being made with, every time I make a recursive call, I'm dividing it by 3. So it's 2t n over 3. Okay. So if I were to write it with the constants, 2t n over 3 plus 4, where did that 4 come from? There is this, multiplication that happened. It's 2. And then there is this addition with the return that's 2. 2 plus 2 is 4. So that's where the non-recursive work is being represented. This is my recursive work with 2 consecutive calls with n over 3. And this is my base case when n is less than 3. Okay? Or you're going to do this, what your colleagues are going to do in future, your peers are going to communicate with you. You will say, oh, you have a base case, and that base case runs in constant time, theta of 1. You have non-recursive work. Non-recursive work runs in constant time, theta of 1. You have recursive work, 2 calls with an n over 3. That's my recurrence. Any questions?
If both recursions weren't n over 3, how would that change your final equation?
Both recursions weren't n over 3?
Yeah,
Oh,
like if
then
they
you
were-
have to, yeah, so that's a good call. Then you have to do t of n over 3 plus t of whatever you're trying to cut the input size by. But that is not recommended because you're really, that's a very funky recursion you're thinking of. You know, it has to be uniform in terms of cutting the data size. Mathematically, we can write it as a model, but that's a really interesting thing you're trying to do, cutting it first by 3 and then that's gonna, I don't know what kind of result you're gonna get out of it. We have never written a recursion like that. Usually you stick with cutting the data size by half or third and you stick with the same constant. Do you see?
Yes, thank you.
Yeah, you're welcome.
Why do we want to have 2 recursion calls in this
Well,
case? Because they look like
yeah.
the same thing.
Yeah, they look like the same thing. Good question. So I don't know what this recursive call is written for. Like I said, it's an example of a recursive algorithm. Why they put it 2 recursive calls depending on the application. I'm going to show you a merge sort. You will see why I'm making 2 consecutive calls because I'm trying to sort something. So the purpose of this recursive algorithm, what it's being used for, we don't know. But it is an example of a recursive algorithm. And all I wanted to do was to be able to model it. Do you follow what I'm trying to say?
Okay, I thought you made it for some purpose.
No, just an algorithm, a recursive algorithm given to you, like in an interview, somebody will say, here's my recursive algorithm. Can you model it? Can you create a code model for me? And then determine its asymptotic analysis. Imagine it like that. We don't know what it's being used for. It's being done for some reason, right? Some application code is using this for some reason. We don't know what it's being used for. It's just an example. Does that help you?
Yeah.
Yeah, you're going to see merge sort and there is a purpose for it. You will see that in a second. Another one, like I said, just to give you an example, the goal is for you to create the model. I'm giving you, and that's what's going to happen in your exam. Again, I don't know what this is being used for. I don't care for the moment. The moment is right now for you to create a recurrence. Here's my algorithm. Take a look at it. There's a typo there. May I just fix it just for a second because I know it's going to bug you. Hold on. The recursion is calling a different function. You're going to say, well, Professor, I say that's not recursion. It's supposed to say recurse to and recurse to. Hang on. I'll go back. Jacob, are you slacking me or is it the TAs? Are you sending me a Slack notification, Jacob? Is Jacob here today? Because I need to ignore it if it's from the other TAs.
Yeah, I'm
Jacob
here.
is the
It's from Andrew. You're good.
Oh, yeah, I'm good. Thank you.
Cool.
Thank you so much for jumping in. Okay. Yes. So there was a typo right here, and I knew it was going to bug you because look, I named my function recurse to, and then I am claiming that this is a recursive function, but it was saying recurse. And I knew you were going to say, well, that's not a recursive function. That's a call to another function. And you would be right. Okay. If I were to model this, somebody gave me an algorithm like this. Imagine you're doing this in an exam or in an interview, whatnot, or you're talking to your peers. They brought their algorithm. I cannot figure out the recurrence. Can you help me figure out the recurrence? You said, okay, let's take a look. When are you stopping your recursion? For some reason, when it's less than 3, you're returning 80. We don't know why, but that's what you're doing. That's your base case. You found the base case. Then you got some stuff going on there. You got a for loop. You're printing I. Okay. Well, that's not recursive work. That's non-recursive work, but that is, you can tell its complexity class is theta of n. All right, so we say that's going to happen n times. And then what? What's happening is you got yourself 2 recursive calls with n over 3. So recurse 2, n over 3, recurse 2, n over 3. They are both assigned. The result is assigned to value 1, value 2. At the end, you're returning the summation of those two. So you analyze what you got as non-recursive. I have this loop and I have this constant n plus 2 non-recursive work. I have my base case and I have my recursive calls. I have 2 plus 2 t n over 3. So I say, if I were to write this with my constants, that's what would it look like, right? It would look like 2 operations when if n is less than 3, and I have a loop plus 2 going on for non-recursive work plus 2t n over 3. Yeah, but in real world, with your colleagues and your peers, that's not what you're going to do. What you're going to do is you're going to generalize it, put the complexity classes. It's going to be more professional this way. So you're going to say, oh, base case, constant, theta of 1. You got a loop, theta of n. This is return with a plus operation. That's theta of 1. And you know your recursion, 2 recursive calls back to back, 2t n over 3. Let me put my recurrence. If n less than 3, constant operation, theta of 1. Otherwise, non-recursive work, this is going to be important, you guys, because you're going to see this in merge sort that I'm about to go into, and then 2t n over 3. Okay, so that is my equation to represent this recursion. I don't know what it's being used for. I don't care. Somebody asked me to generate the function. I just did. Now, the next step is somebody's going to ask you, solve it. Solve and tell me the asymptotic analysis. Good for you to generate the recurrence. It's always quite tricky to generate the recurrence. You did. Now solve it and tell me, as my colleague, what kind of runtime complexity am I in when I write a recursive algorithm? Did I just write something 2 to the n? Am I going to lose my job over this? You know, just to add drama there, right? So yeah, basically, I can go on and on and on like this. Like I said, there's another typo I just found there. My goodness, people don't know how to make recursive calls, I tell you. Let me save this because I got updated on D12.
That's a good background.
Oh, thank you. Yeah, I get a lot of compliments for that. And it all belongs to OS, by the way. I have never been to that place. It's not a vacation picture, okay? So here I had the typo. I didn't want you to see that. It will look not good. It looks like a function call then. So I fixed that. Recurse 3, recurse 3. So here's a recursive function. N is less than 3, return 80. You got a loop. 3 recursive calls with n over 4 this time. And you got some algebra going in at the very tail end with multiplication and addition and the return. So we start analyzing, looking at the non-recursive work is a linear operation plus n, you know, it's a n plus 3, I want to say. Recursive work is I have 3 consecutive calls with n divided by 4 this time, and the base case is a constant. If I were to represent it with the constants, if n is less than 3, it's 2 operations that I have to take care of. Otherwise, n plus 3 non-recursive work with 3 recursive call with n over 4. Okay, we could do it like that, or I gotta fix the slide too, but I'll do that after lecture. Or I can just simply represent it in general terms, and I can say n is less than 3, theta of 1, a linear operation that runs in linear complexity n plus 3, drop the constants, drop the lower order terms, don't forget. So n plus 3 is considered to be theta of n. We don't care for that plus 3. Now, do you understand? I don't really care for those plus 2s and plus 3s. It makes no difference for me as long as I find the dominant term. Dominant term is n. That's n plus 3 is a polynomial of a degree of 1. So if n plus 3 is the polynomial, drop the 3, it is theta of n. So that's why you see me dropping all those 3's and everything and just representing non-recursive work as theta of n. And then 3 recursive calls with 3 times t n over 4. Any questions here while I go and fix that? I should make it sure that it is recurse 3, so it's making the correct call. Any questions here?
So how fast should we be able to look at a small block of code and then write a model
Recurrence?
for it?
Yeah.
Yeah.
How fast? It doesn't take too long. How long did it take for you to figure this out in your head? Were you able to
Well,
follow what I was telling you?
I just looked at when it was calling the function and then saw that it called it 3 times and the n/4. So
You kind of figured that part right away, right? 3t n over 4, right? And then
the other stuff doesn't matter.
Yeah. So what you're going to do, very good question. Thank you for asking that. I'm glad you guys are thinking this. It doesn't take too long. It gets tricky though. As the algorithms get a little bit more tricky, it gets tricky, but it doesn't take too long. The number one job you're going to do is, how do I stop it? When do I stop it? Am I stopping it? Yes, I am. When n is less than 3, as the input size shrinks, n is less than 3, stop. So did I have a base case? Yes. How is it growing? Well, it's growing constant, theta of 1. I got that. How am I calling this? Am I calling this consecutively more than once? Yes, I am. And how am I calling it? Am I calling it by subtracting the data by 1? Or am I calling it by dividing the data size, input size by some value? Yes, I am. I'm dividing it by some value, n over 4. 3 times. 3t n over 4. T n over 4 is your first call. That's your call, your recursion call. And I have 3 of them. That's why you see 3 in there. Do I have any non-recursive work? Yes. It appears that I'm printing something in theta of n, and it appears that I'm doing some algebra. But that doesn't matter because printing something will dominate over that algebra. Like I said, n plus 3, n is the dominating term. Drop that and then assign it as theta of n. It won't take too long. What you're going to find out when you get to the end of the semester, you will become the master of it because we're going to give you a lot of algorithms. You're going to constantly analyze it. It comes with practice. Okay. So try to play with that. So the tool chain has been completed. Now I looked at my algorithm. I came up with a recurrence. Using the recurrence, I will do the asymptotic analysis. Okay. So one thing you notice probably, I got a recurrence like that, one of my examples like that. Okay, so that's great. I'm happy for you. You do have a recurrence, but can you tell me my asymptotic analysis? Well, I couldn't. Binary search was so easy. I said, well, this is logarithmic. Anybody coming from the logarithmic background can see that. I'm cutting the data size by half. But what if it's not like that simple? I have 2 consecutive calls with n over 3. What's my complexity? So I'm introducing you now the master theorem. Master theorem works only if and only if you have a recurrence of this form. It has to be that you have a base case, obviously. You have to have base case for all recurrences, but your recurrence has to have a form where you're cutting the data size by something, not subtracting. Okay, so you cannot have a recurrence where the recurrence is happening with t.
Wait,
open.
Professor,
Yes.
can you just repeat what you said? Like you broke out a little bit. Like
Oh, I broke out. Okay.
Yeah.
Okay. Thank you for letting me know. We're going to talk about master theorem, and master theorem can be used on any recurrence that contains this form. Is it breaking?
Yeah, it's still breaking.
Okay. I'll sign out. I'll sign back in. Stay in here. Okay.